Good morning, children. You are able to hear me and see the slides, right? Okay. So we look into the ATPG, that is automatic test pattern generation. The tutorial sheet was uploaded in your assignments. You can open it from there. The question number first. You are given a particular circuit which had two AND gates. And you had three inputs. A, B, C, the stuck at zero fault here at D needs to be detected, and you were required to find the test pattern which will detect this, right? Your question said that determine the test vector generated by ATPG to detect a stuck at zero fault at the net D in the given circuit using Boolean difference and D algorithm. If the method is not mentioned in the question, you are free to use either of the three methods. The three methods that we did are D algorithm, the Boolean difference, and the path sensitization method. So you can use any of the three. Here you are asked to find the test pattern using the Boolean difference. So we look into the first procedure, that is Boolean difference. Boolean difference says that the output Z without fault when XORed with the output Z with the fault which is modeled should always be true. Because we already said Z will never be equal to ZF. The faulty output will always be different from the non-faulty output. Therefore, only one of the two things will always be true. Hence, Z XOR ZF will always be equal to 1. So, when we are trying to work out with Boolean difference, we try to find the expression of Z, put in the condition of the fault and find the new ZF. For example, Z is the output, which is E here. So E can be expressed as AB and C, right? This is E. What is EF? The faulty output F. Faulty output, the faulty output E will always be equal to 0, right? Because D is stuck at 0, so one of the input of this AND gate is stuck at 0. So the output E will always be 0. Hence my expression becomes ABC XOR 0 equal to 1, which means ABC into 0 bar plus 0 into ABC ka bar will always be true, which simply means this is small abc. ABC equal to 1. This simply means that the test vector which is required to detect this fault will be given as A equal to 1, B equal to 1 and C equal to 1, because if the three inputs are 1, then only A dot B dot C will be true. Is it okay? The Boolean difference? So we have this as the test vector which is required to be applied at input to detect this fault. Now we try to do the same thing with D algorithm. Boolean difference is useful when the circuits are not very complex, because we need to find the value of Z. If there are so many gates applied within the circuit, the expression for Z will be very long, right? D algorithm works on three things: the primitive D cube for the fault, the propagation D cube, and the singular cubes or the primitive cubes of the logic gates. You need to remember how to find this PDCF, PDC and singular cube for any logic gate from the truth table. The steps would be, the first thing is you find out what is the primitive D cube of the fault. For example, here primitive D cube will be obtained for the gate G1 because the output is seen to be faulty at D. Hence, I find the PDCF for logic gate G1, which simply means that what should be the value of the input AB so that the output D is always stuck at 0. Since this is stuck at 0 fault, whatever be the input at A and B, D will always be 0. Hence, A and B are X, that is don't care. So, PDCF for gate G1 will have the value of A as X, B as X and D as 0. The next thing is to find out how are we going to propagate this fault towards the primary output. So the logic gates which lie in the path for the propagation of the fault towards primary output are referred to as the D frontiers. The gates through which the fault D propagates in the form of D or D bar. This is D, in the sense that the actual value is 1 but the faulty value is 0. So this is represented as the variable D. In order to propagate this D to primary output, I need to look at the gate G2. So I will find the propagation D cube for gate G2. PDCF is obtained for G1. That is, this is my D frontier. Right? To obtain this PDCF, I need to look at the singular cube of this gate, that is your AND gate this is. So I put the inputs as D, C and the output is E. So if you remember your AND gate, AND gate का singular cube क्या था? 0x gives you 0, x0 gives you 0 and it is only 1 1 which gives you 1. So now I consider this part as alpha, this part as beta, and I take the Roth intersection for each of the element, right? So here 0 intersection 1 क्या होता था? What was 0 intersection 1? Zero intersection 1 was D bar. D or D bar, these are interchangeable. So 0 intersection 1 is D bar. Therefore, I write the PDC as this is D bar. Then X intersection 1 is 1. 0 intersection 1 is D bar. Similarly, for the second set, X intersection 1 is 1. 0 intersection 1 is D bar. And 0 intersection 1 is again D bar. So this gives me the PDC of G2. Had there been any other gate lying which is not used for the propagation of the fault, we could have used the singular cube for that logic gate. Right now it does not occur here, no other gate is here. Therefore, we need not consider any other singular cube. Suppose there is more than one path towards the primary output. Then we will choose at least one of the path initially and try to work out for the consistency check If consistency is there for the inputs, then fine. If not, we will backtrack and redo the work with the other path available towards primary output. Right? We'll look into that question. For the time being, I write all the values of the net A, B, C, D, E and try to do the consistency check starting with the PDCF of gate G1. So A is don't care, B is don't care and D is 0. I simply write the values obtained for the inputs and the outputs for the logic gate. The second time, I use PDC of G2 such that at least one of the values is consistent. But here none of the values is consistent. D is D bar 1 and C is 1. I could have 1 D bar and D bar, or I could have D equal to 1, C equal to D bar, E equal to D bar. Since there is no consistent value in C, B and A are don't cares. Therefore, according to D algorithm, the fault stuck at 0 at D cannot be determined. Right? So we need to backtrack. We need to drop this fault from the set for D algorithm and require to consider any other fault, so that we find the first test pattern which may sometime detect this fault as well. Because a single test pattern can be used to detect multiple faults. Right? This consistency is very important. If the consistency is not coming out, we do not have any consistent values for the primary inputs. In that case, we say that the test pattern cannot be detected. Right? So Boolean difference said that this will be detected by 1, 1, 1, but D algorithm does not give me the same output, and it says that due to the inconsistency, the fault cannot be detected. Right? Now look at question number 2. This is an important thing here. I'll not solve all the questions, just quickly revising the algorithm and leaving up to you to practice these questions. And somehow I missed the question on sequential part here. I'll upload it today. This is all the combinational circuit. What is the last gate? Not OR gate. X1, X2, X3, X4. And you are required to detect a fault here which is stuck at 0. The gates are labeled as G1, G2, G3, G4, G5. Now Boolean difference you can simply do, you can find the expression here, put the value of this output, that is x2 and x3, as 0, and then analyze to find the new value, the faulty value at this wire, let us say the output Z, right? Let's talk about the two parts for D algorithm. When I start here, I will first find the PDCF primitive D cube of the fault for gate G2. Now this fault can propagate either through this path or it can propagate through this path, right? So initially I take the path, or I take the D frontier with G3 and G5. When I consider this D frontier with G3 and G5, I try to find the PDC, the propagation D cube for the two logic gates G3 and G5. And I take the singular cube for G2 and G4. And using these, I perform my consistency check. If I get consistent value for my inputs, well and good, that is acceptable as the test pattern. If not, if no consistency is found, then what we do? We choose another D frontier path, which will include G4 and G5. So now my step would be, I still take PDCF of gate G2, but now I take PDC for the D frontier consisting of G4 and G5, and I will take the singular cubes of the rest of the gates, that is, this was G1. This is G2. So PDCF of G1, the AND gate, PDCF of G1. Singular cube will be taken for G2. This is the leftover gate, and G3. And now for these, I go for consistency check. Right? This process of finding the next path or using the next path is referred to as backtracking. This is generally the issue with the D algorithm, because if there is a single path, then fine, we know the path which is required for the propagation of the fault. But if there are multiple paths, we may fall into the trap of backtracking. Multiple paths में किन्हीं तीन paths से नहीं detect हो पा रहा है, so every time we'll analyze for those paths, backtrack, analyze for the next path. If it is not giving out consistent value, again backtrack, and the process will be continued. Right? So backtracking is an issue when we are working with D algorithm, but nothing can be done as of now. We need to have the analysis done beforehand, so that we can minimize this backtracking during the execution of algorithm. Right? The third process was path sensitization method for ATPG algorithm. Path sensitization method simply means you need to first initialize the fault, then you need to propagate the fault to primary output, and then justify the values to primary inputs. Right? So we'll initialize the fault stuck at 0. It means the value should be 1, 0 here. This is what is meant by initialization. So while answering the question, you will simply say that as the first step, the fault is initialized. So the output of the AND gate G1 is expected to be 1 in non-faulty case and 0 in the faulty case, which is written as 1, 0. This output needs to be propagated through the NOR gate G3, right? So to propagate to the primary output through G3, the output is required to be D only when the other input is 0. Other input of the NOR gate is 0. तो 0 और 1 होगा तो आउटपुट विल बी 0, और अगर 0 0 होगा इनपुट तो आउटपुट विल बी 1, right? So I'll have the output, the fault propagated in the form of D bar. Is it correct? 0 1 पर 0 होना चाहिए और 0 0 पे 1 होना चाहिए NOR गेट का. So at the output I will have D bar. Fine. To propagate this towards primary output, I need to set the values for the inputs at G5. So if I want this D bar to propagate towards primary output Z, the other input of G5 needs to be set equal to 0. So that when the inputs are 0 0, the output is 0, but the inputs are 1 0 for this G5, the output will be 1. So Z is unequal to the faulty Z, that is ZF. Right? This is the propagate step. Now to justify. Propagation has been performed, the fault has been propagated to output. Now moving back towards primary input to justify the value of 0 at the output of gate G4. When one of the input is set to D, I need to ensure that this value is 0. So the other input of this AND gate should be put equal to 0. So that irrespective of the value here, the output is always equal to 0. Further moving towards primary input X4, if the output of the NOT gate is required to be 0, it is justified only when the input is put equal to 1. Hence, X4 equal to 1. इतना सब लिखना पड़ेगा, खाली ये ग्राफ पर अगर लिख दोगे तो I will not give you marks. Fine. Then comes justification for this. For the output of gate G1 to be non-faulty 1, I need to ensure that the inputs are 1 1. Hence, X2 equal to 1, X3 equal to 1. The input G3, that is X1, which is input to G3, is already set to 0. Hence, the test pattern required to detect the fault using path sensitization method comes out as 0 1 1 1. Is it clear? Now you can practice for all the 4 circuits for all the 3 algorithms. The D algorithm, the Boolean difference, and the path sensitization method. I hope it will not be a problem anymore. If you have problem, you can ask me personally. Anything else here in ATPG? सुनाई दे रहा है? Dhanush? I'm not able to hear if you are answering.
Ma'am, you're audible.
Okay. Now look at the assignment for the 4th tutorial. The rest of the question I'll leave it to you. If you want to do, you can do. Where is my assignment? Okay. Tutorial 4 was on SQAP measurements. That is, you were required to calculate the controllability and observability for the circuits. Looking at the first circuit, A, B, C, A, B, C, A dash, D, E. You have to find the controllability and observability for each of the wires. So to find the controllability first, we initialize the controllabilities for primary inputs. What is the initial value of the controllability for the primary inputs? जीरो होता है या 1 होता है? You have a quiz on Sunday at 12 for the SQAP measurements. So we initialize the primary inputs with the controllability of 1 for CC0 as well as CC1. Therefore, the primary inputs are initialized with 1, 1. So the value of CC0 and CC1 is 1, 1 for all the primary inputs. Then we propagate this, then we move forward and try to calculate the controllability for level 1 gates. The level 1 gates are all the gates which are directly connected to the primary inputs. Right? So this is my level 1. Level 2 will be the logic gates which take the input from level 1. So here I have the NOT gate at level 1. The output of this NOT gate is given as input to the AND gate. So AND gate is referred to work at level 2 or depth 2. Then I have level 3. Level 3 gates will be the gates where at least one of the input is obtained from level 2 gates. So here D is coming from level 2 gate, therefore this is level 3. So when we are trying to find the controllability, we will analyze all the logic gates in a particular level before moving on to the next level. So here I have the first level logic gate as the NOT gate. So I'll try to find the controllability at the output of this NOT gate. The controllability are given using the formula. The output controllability controllability for each level. Output controllability is given as the minimum of input controllability plus 1 if setting one of the input is sufficient to control the output, right? अगर एक ही input से sufficient है, then we take the minimum of input controllability. But it will be equal to sum of all the input controllabilities plus 1 if all inputs are required to be set at non-controlling value. ठीक है, this is the general rule for calculating the output controllability, right? If I want to have the output here controlled equal to 0, I need to have 1 at the input, right? और अगर मुझे यहाँ 1 लाना है तो मुझे इनपुट पर 0 होना चाहिए. It means it is only one input which is sufficient, which is required to be set at the input so as to control the value of output. Therefore, the controllability is again given as 1 1. But if I look at the second level, that is your AND gate, now this is 1 1, this is also 1 1. So if I want to find out CC0 at D, which means to set D equal to 0, at least one input of AND gate is required to be set to 0. Hence, D ka CC0 will be equal to minimum of input controllabilities plus 1. मिनिमम कंट्रोलेबिलिटीज क्या है? 0 सेट करने की, इसकी 1 है, इसकी 1 है. Therefore, minimum of 1 comma 1 plus 1, which gives me 2. So CC0 at D will be equal to 2. Similarly, you will write for CC1. CC1 means you want to set the value of D equal to 1. If you want to set the value of D equal to 1, both the inputs of the AND gate are required to be set equal to 1. Therefore, you should take the sum of the input controllabilities. Sum of input controllabilities to be set equal to 1 is this 1 plus 1 and plus 1 for the next level. So this gives me 3. So the controllability is given as 3 for wire D. Is it clear? Similarly, you will proceed for level 3 as well. Right? This is about controllability. For observability, you work in the opposite way. Opposite way in the sense that you move from primary output towards primary input. So this is my primary output. So now instead of initializing the primary input, we initialize the primary output, but the initial value of the primary of the observability at primary output is 0. Right? Observability can be calculated backwards. Once I have the output observability, I can determine the observability of each of the inputs for the logic gate using the formula that the observability here, let's say C0 will be, how do we write CO? So CO. So observability will be given as the observability of the output plus the CC0 or CC1 of the other input when required to be set to non-controlling value. ये मेरा OR gate है. OR gate का non-controlling value क्या है? 0. Right? So whatever is CC0 here, that will be added to the observability of the output and plus 1. That gives me the net observability at this wire. Finally, giving the observability at this wire would be output का observability plus CC0 या CC1 of the other input. वो कैसे decide करते हैं कि कौन सा non-controlling value है. So the non-controlling value is 0 here. Therefore, CC0 of this other input will be added to the primary, added to the observability of the output plus 1. That will give me the observability of this wire. The observability will always be written outside the brackets. Then you propagate, then you move back towards primary input and continue until you get the observability defined for all the wires. Okay? I'll put up the sheet for sequential circuits. I somehow missed it here. You are given 4 circuits here and you are required to calculate the controllability and observability for each. Here you have the sequential circuit also given, one sequential circuit. So जब sequential circuit होता है, then initialize all the controllabilities act as infinity, right? You initialize all the controllabilities as infinity for each line and try to analyze just like we do for a normal combinational circuit, but you will keep on repeating the process until you get the values constant for each of the wire, right? So you will do it multiple times until you get constant values. Once you get the constant values of the controllability, all the infinities may go off, and that would be the point where your final controllability will be assumed. Okay? Try to do these questions, both the tutorial sheets. Any problem in any of the topic for your sessional examinations? They are beginning from 25th. Any problem? Any specific problem? When do your exams begin? तुम लोग मुझसे कभी फिजिकली पढ़े हो? नहीं पढ़े ना? I have one very simple rule. If you do not answer me, I am not liable to answer any of your query. Remember this very well. I very well stick to this theory. If you do not respond to me, I am not liable to respond to you. You cannot ask me anything then. Whatever marks I'll give, that will all be final. I will not be liable to answer to any of your questions regarding any subtraction of the marks I do. Okay, so that is all from my side for your midterms. The syllabus is the entire thing that we have done till today. Everything will be coming in your midterm examination. From the next class, we will begin with the memory test. Anything you want to ask, you can add, else you may leave.
मैम एमटी में भी ऐसे ही क्वेश्चंस आएंगे जैसे आप
हाँ जी, ऐसे ही आएंगे. इसीलिए आपको प्रैक्टिस कराया है, इसीलिए आपको क्वेश्चंस दिए हैं. यू कैन प्रैक्टिस इट वेल. Only Purva has uploaded the sheet after solving the questions. I'll check it, Purva, today and return it back to you.
Okay, ma'am.
If anyone else wants to get the answer sheet check, just upload it in the assignment. You asked me something, Purva. I told you I'll tell in the next class. What was that?
Ma'am, how to write the answer for fault dominance?
Fault dominance, yes. Fault dominance का जब भी question आएगा, so you just look at the circuit. For example, you had a circuit with the AND gates, OR gate, and a NOT gate. This was the question from your assignment or the tutorial. In such cases, do not directly start working with the circuit. Instead, before first write that for a NOT gate, the input stuck at NOT gate के लिए तो कोई dominant होता ही नहीं है. Input stuck at 0 is detected with input stuck at 0 will be detected as 1 0. So your input will be 1. The output stuck at 0 is detected with input set 1. Input stuck at 1 is detected with 0, and output stuck at 1 is detected with input 1. Output is stuck at 1, so this is 1. Output stuck at 0. ये 1 0 होना चाहिए. So now your dominancy says कि input का जो test pattern है, test vector है, this should be able to this should be a subset of the output test pattern, right? So stuck at 0 is a subset of stuck at 1 at least. Therefore, the two faults are dominant. The stuck at 1 fault at the output is dominant. But dominance से पहले तो हम equivalence check करेंगे. तो equivalence में input पे fault हम remove ही कर देते हैं. For equivalence, stuck at 0 at input is equivalent to stuck at 1 at output of a NOT gate. Since the test patterns is same for both the faults, therefore we drop the stuck at 0 at input. Similarly, stuck at 1 at input is equivalent to stuck at 0 at output, therefore we eliminate stuck at 0 after equivalence. So NOT gate में मुझे केवल मिलेगा stuck at 0 at output and stuck at 0 at input for dominancy check. So dominancy check में I should eliminate this input faults. ये तो equivalent की वजह से collapse हो गए. Now I am left with these. So the two cannot be dominant. So both of them exist. Right? Therefore, I will say here I will have stuck at 0, I will have stuck at 1, both existing. Similarly for AND gate, पहले equivalence के लिए check करो. For AND gate, stuck at 0 at input is equivalent to क्या stuck at 0 at output. चेक करो उसमें नोट्स में क्या है.
Stuck at 1 at input.
Stuck at 1. ओके एंड गेट ऑपोजिट होता है. हाँ ठीक है. It is equivalent to stuck at 1 at output. Hence we collapse the stuck at 0 fault at input. दोनों क्यों होते हैं? क्योंकि stuck at 0 के लिए टेस्ट पैटर्न लिखे होंगे हमने और stuck at 1 के लिए टेस्ट पैटर्न लिखे. The same test pattern will be able to detect both the faults. Therefore, we say that the faults are equivalent. So we collapse the stuck at 0 faults at input. Right? तो stuck at 0 fault यहाँ से हट गया होगा. ये नॉट गेट के आउटपुट पर तो एग्जिस्ट कर रहा था, बट देन इट विल बी एलिमिनेटेड ड्यू टू दिस रीजन फ्रॉम द इनपुट ऑफ माय एंड गेट. डायरेक्ट सर्किट पर नहीं लिखना है, यू नीड टू राइट इट डिफरेंटली, जस्ट वंस फॉर ऑल द गेट्स. जैसे यहाँ 2 बार एंड गेट है तो 2 बार लिखने की जरूरत नहीं है. फॉर एन एंड गेट दिस इज द केस दैट स्टक एट 0 एट इनपुट विल बी एलिमिनेटेड ड्यू टू फॉल्ट इक्विवेलेंस. Hence you simply write stuck at 0 and strike it off due to equivalence. Right? Then you do the same way for dominance. ऐसे लिखो and simply redraw the circuit and eliminate the faults due to dominancy now. ठीक है? Need not work for every logic gate. Just make some statement, make a statement for every type of logic gate in your circuit and then use that statement. Similarly, when you are writing the solution for deductive fault simulation, do not just directly write the set of faults. Write it in the form of unions. For example, if I have the fault list of B defined as fault list of A union, I should say fault list of C minus fault list of D. I should write this step first, then I'll write what is the answer. What are the faults that are in fault list for LA? What are the faults which are in LC? When subtracted LD, what is the final list of faults that need to be considered? Do not directly write LD is something like A0, B1, C1. This will give you half a mark only. How do you get this? How do you obtain it? From what step? Main marks are for this. इसके बाद ये तो कोई भी लिख सकता है. The thing is, how do you write this? How do you deduce this? That will fetch you marks. This will not give you much marks. ठीक है? Still you have time. Start practicing and ask if you have any problem. Anything anyone wants to add? You still have 3 days, 3 classes left. I do not have anything to be revised now, so I'll start with memory testing. If you want anything to be revised, you let me know. Okay, that is all from my side for today. You may leave. And you have a quiz on Sunday 12 p.m. on square measurements. I'm ending the meeting now.